Right, welcome class to this session on the basics of heterocyclic molecules. Now, today we're going to take you back to some basics on the organic chemistry molecules. What I've put on this whiteboard is something which you've encountered before, but want to lay emphasis on the molecular orbitals. Uh, um, as you're aware, this is a covalent bond, and a covalent bond you're going to say um, is going to be shown uh, as an overlap of a head-on overlap uh, uh, of two orbitals. In this case, it will be a p orbital of carbon and an s orbital of hydrogen. So for example, okay, let me just try to see what I can show you a molecule. Like, can you be able to see on the board this tetrahedral molecule, which I'm going to show us as your methane. So the bond angles are 109.5, and it's tetrahedral. It means that if I'm just going to put it flat, you're going to see there will be there will be a what? There will be a triangle at the bottom, and then there's this apex here. So it's like a tetra pack. Yeah. Can you be able to see well? Now, uh, so you're going to see that the atoms, I mean, or the orbitals which carbon uses for bondings are the sp3 orbitals, which are just going to be shown as these dumbbells here. Carbon has got how many? Has got 4 sp3 orbitals if it is saturated. If it has one double bond, it has 3 sp2, and if it has 2 pi bonds, then it has 2 sp orbitals. One bonding with another carbon. You're talking about like this. Can you be able to see on the board? So the thing is, the orbitals here are going to be sp hybridized, but for double bond there will be sp2. So let me just delete that one because there's something I'm just trying to illustrate about carbon here. So for simplicity's sake, is that to avoid complicated structures, I'm just going to show these two bonds as this carbon. This is the sp3 hybridized orbital, and then the carbon which is bonding is spherical. No, hydrogen. Hydrogen, the atom is. I mean the orbital which is bonding for the hydrogen is a 1s. So it's just being shown as a sphere here. So the hydrogen will be shown as a sphere. This is being shown as a sphere. For simplicity case, I can show the same thing for here and here, but it will be complicated. So these are the two which I'm just going to show here, but for the so these two are just being shown the way they are, and then these are the ones which are just being shown here. So can you be able to see here? So this is the orbital for carbon. This is the orbital for carbon for this one. The hydrogen is being shown as the spherical hydrogen. This is being shown as the spherical hydrogen. Yeah. So so this just like can you be able to see well on the board? Oh, I believe you can be able to see well. So this is just the general atom which is being used for the bonding. So this is your hybridized orbital. So this is the side which is bonding. This is the side which is being hidden. It's being shown as a small lobe, yeah. So it's just being shown here. So if this atom, it will be bonding with the hydrogen. So I'm going to show my hydrogen here, and then I'm going to put a spherical, yeah. So this was just being shown here. So the atom here can be carbon, nitrogen, oxygen, sulfur, or fluorine, or something like that. Yeah, yeah. So this just like a generalized illustration there. I'm just giving you an overview of what you learned in in level one if it is ODL, or in first year if it is uh, uh, fourth year uh, uh, for the other courses here. Okay, so carbon forms four bonds. So if it is filled, it means that it's going to have four bonds, which are each bond is two electrons. So I'm going to show 2, 4, 6, 8. Yeah, this just uh, showing the electrons without any bonds. So this is a filled orbital. When the carbon, in this case, uh, this is going to be neutral, or in this case, you can also show. I don't know whether it can be seen well, like a carbanion here, whereby these are two electrons, two electrons, two electrons, and then if it is carbanions, then the two electrons are in the lone pair. So this is filled orbital. But when it is vacant, then whatever was subtracting the electrons, like the base, goes away with the two electrons, so you'll be left with a vacant orbital which will be positively charged. Okay. Now this positive charge is what you're going to be showing as your as your orbital. So for example, in this case, I can illustrate as carbon here. There's a hydrogen, there's a hydrogen, there's a hydrogen, and then there's a plus here. So that is a carbocation, yeah? The one which I've shown here. Let me just try to see whether I've got a suitable case here. Can you be able to see here? Now, this red and the blue are the ones which are shown as the sides of the orbital. So a carbocation is flat, yeah? So if this is the carbon, then the hydrogens are flat on a plane, and then the empty p orbital is coming out of the plane, yeah? So this is being shown as your carbocation. So how am I going to show it? Okay, let me just try to, excuse me, let me just try to illustrate here once again. So you've got your carbon here, there's a hydrogen, 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 and then you've got your p orbital, both top and bottom, yeah? Can you see that? So these ones are lying on a plane. Excuse me, they are lying on a plane. Oh, excuse me, there's an atom here. Let me just try to get a small atom of hydrogen. Oh, good. I've seen a small atom. It had just fallen off. Let me just try to put another. Excuse me for that. Okay. Excuse me. So this is the same thing, yeah. So this is your metal cation. Though you know it's unstable, yeah. So this is your carbon, hydrogen, 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 and this is your vacant orbital. It's not being shown to size because the p orbital will not be as big as that one, yeah. But just showing that the vacant orbit, the p orbital, uh, for example, if if this is your xy axis, yeah, yeah, uh, the plane of where the carbon and the hydrogens are lying on the plane. Yeah, what I'm just trying to say, this is a plane which is flat. Yeah, these atoms are flat, so you can say they are in xy plane. So the p orbital is coming along the z axis, which say it is perpendicular to the plane of the molecule. Can you see that? There is the xy axis, and then there is the top bottom, which is the z axis. So that in this case, we'll just be saying in general, the p orbital, if it is one p orbital, then it will be along the top bottom axis. So regarding that one, I think it's worth mentioning here. Uh, Now, what can you see here? Now, this is this is an alkene molecule. Okay. Now the purple ones, I'm using different colors. Like the purple ones are now the carbon in this case. Now the hydrogens are lying on the plane. Can you see here? There is a plane here which I'm showing flat. So the carbon and the hydrogens, they are lying flat on the plane, and then the p orbitals on this carbon, they are top bottom. So on these other ones, they are top bottom. So can you see here? So there is this is one p orbital. This is another p orbital. Yeah, it's in this case it's along the z axis. So this is an example of an alkene. Can you see here? The bond angles are 120 degrees. Yeah. Okay. So this is your p orbital. So this is the one which are showing as your as your uh, as your double bond. These are the molecules which you are going to be dealing with under unsaturated heterocycles. Now, how about a triple bond? A triple bond is made up of two perpendicular uh, pi bonds. Can you be able to see well? So what you're calling as your triple bond is actually made up of two perpendicular pi bonds. Can you see in this case here? So there is a so there is a So there is a pi bond along the z-axis, and there's another perpendicular. There's another one along the y-axis. So the hydrogens are along the x-axis. Can you see there? So this is the x-axis for the. So this molecule is linear. It's just being shown here. So the carbon here, and then the hydrogens. So this is linear. So this uh, can you be able to see here? So you've got one set of p orbitals which is along this axis, uh, the z-axis. The other one is along. So this one along the z-axis, the other one is along the y-axis. And please note this: perpendicular p orbitals do not interact. So an atom can have an electron density on this p orbital and another on this p orbital. But because it's at 90 degrees, this p orbital and these p orbitals do not interact. By interacting, it says that the electron density cannot cross over to this other atom. You're going to see when you're going to be dealing with with conjugations, like in this case here, for this electron density to be shared, these two atoms must be aligned parallel. Like, like these two atoms, they are aligned like this one. So this electron density can be passed to here because they are parallel. So if you have something like this one, which is at maybe at an angle of 30 degrees or 60 degrees, there is no electron density which can be passed because they are not on the same axis. Can you see that? So for them to share the same electron density, they have to be on the same, they have to be linear like that. Now this one usually happens when you're dealing with aromaticity, that the orbitals have to be on the same axis. For electron density to be shared, the p orbitals must be along the same axis. Please know this. So if it is not going to be on the same axis, like in this case here, then this p orbital and this p orbital, they are not going to the electron density is not going to be shared. Okay. Now, good. Are you following? Very well. Now, let's look at oxygen here. Oxygen here is being shown as uh, as having a filled shell, has got 2, 4, 6, 8 electrons. Oxygen forms two bonds, yeah? So in this case, like in the case of water, uh, the two electrons have been used in forming oxygen-hydrogen bond. In this case, the oxygen-hydrogen bond on this other side. So we'll be left with two electrons here. Now, even though I've drawn it like this one, actually a water molecule is tetrahedral. It's not linear. So what I'm going to do is that I'm going to show the water molecule as it exists here. Uh, Pardon me by showing very big uh, uh, lone pair or the p orbital containing the lone pair. So the red one is being shown as the oxygen, and then these are the hydrogens. Yeah, yeah. So the thing is, if I may show like this one here, it means that okay, if I may show it like this one, then one of the lone pairs is at the top, the other lone pairs is on this other angle, and then the two hydrogens, they are forming the part of the tetrahedral. Can you see the tetrahedral? So one of the lone pairs is forming one side of the tetrahedral. So oxygen, so water is tetrahedral. Uh, Now this illustration is important because when you're going to be showing the lone pairs as attacking an atom, you're going to say the lone pairs will be coming from this p orbital. This p orbital is where the electrons are going to be coming from. Yeah, are you seeing that? This p orbital is where the electrons are going to be coming from. Now, let us look at nitrogen. Nitrogen has got, once again, when it is filled, has got 8 electrons, 2, 4, 6, 8. Now, nitrogen forms 3 bonds. So for the 8 electrons, it means that one bond it will be 2 electrons, another bond it will be 2 electrons, another one it will be 2 electrons. So the nitrogen is going to be left with one lone pair. So this is what is just going to be shown here. It's also going to be, if we're going to have something like ammonia, it's going to be tetrahedral. Can you see that? So the lone pair is being shown as your p orbital here, and then the other hydrogens, the hydrogens on the attached to the nitrogen will be forming part of the tetrahedral structure. Can you see that? If I've got it flat like this is going to be flat. Can you see? It's going to be like a tetrahedral. Nitrogen like that one, ammonia, and then your lone pair. So this the lone pair which will be sharing electrons is being shown here. So when you're going to be showing the nitrogen becoming like a base, the electrons will be coming from this p orbital, which is being shown as your p orbital here, the lone pair there. Okay. I don't know. Okay. I think before I take a break, I need to show here that okay. I don't know whether it can be seen well. Um, in this case, I'm showing a carbanion here. So the thing is, the carbanion on the carbon is still tetrahedral. So the lone pair are on the p orbital. Are on the p orbital. The same thing here. Uh, uh, Now this hydroxide ion, compare with your water, it means that it has lost one hydrogen. So the hydrogen has moved as a proton, so it has left 2 electrons. So these 2 electrons were initially from the bond between your oxygen and your hydrogen. So it's now becoming your lone pair. So in this case has got 3 lone pairs in the p orbital. This p orbital, this p orbital, and this p orbital. Yeah. So when you're going to show your hydroxide actually contains 3p orbitals containing 3 lone pairs. Yeah. Also, when the nitrogen, when the ammonia which you had here also loses a hydrogen to become an anion which are going to call an amide. So in this case, nitrogen initially had 1 lone pair. So if this one is lost, you're going to get your second lone pair. So in this case, your amide is going to have 2 lone pairs. Yeah. Once again, I'm going to be illustrating this one later, but this just to show you the use of the orbitals in organic chemistry mechanisms. I think it's the first time I'm introducing this to the fourth year heterocyclic chemistry, but I'm seeing this thing of showing a curly arrow moving like this one. A curly arrow is just like an illustration of how the electrons move, but what you really have is actually the interaction of orbitals, which is what you're going to be focusing on. Interaction between the orbitals, like in this case for the p orbitals, for nitrogen and for oxygen, and maybe like the hydrogen showing the s orbital, or maybe another p orbital for carbon, oxygen, something like that. We're going to be seeing interaction of those orbitals in addition to the curly arrows. I hope you've really enjoyed. This was just like an introduction. It was just about 20 minutes, and I hope you've really enjoyed this session. So you're going to stop there, and then in a short while, we'll go to the next session. Thank you. Okay?